Hi, my name is Janick Weberpals, and I'm the lead author of the study Deep Learning-Based Propensity Scores for Confounding, Controlling Comparative Effectiveness Research, a large-scale real-world data study. This study was initiated as part of my postdoctoral fellowship program in the Data Science Division at the Roche Innovation Center in Munich, PRI, together with colleagues from the Institute of Computational Biology at Helmholtz Center, Munich.
So, as opposed to randomized trials in observational studies, we may acknowledge the fact that due to the lack of randomization, there will be likely systematic differences in baseline characteristics between patients who received the drug A versus patients who received the drug B. As a balancing score in pharmacoepidemiology, these systematic differences might be approached using propensity scores, which are defined as the conditional probability that an individual receives a certain treatment based on observed baseline characteristics. Now, causal inference theory tells us that by conditioning the two cohorts on the propensity score, for example via matching or weighting, the only remaining difference should be the treatment itself. Now, as with all statistical models, also propensity score models underlie assumptions that include, for example, also the modeling of nonlinearities and non-additivities, which need to be considered. Some deep learning models, such as autoencoders, entail some interesting properties that may help with the aforementioned challenges in an automated fashion. Autoencoders are popular neural networks in the field of computer vision and usually comprise of an input layer, a bottleneck layer, and an output layer, and potentially some hidden layers in between. Now, if you think of a dataset as a one-dimensional input layer, where each covariate or feature represents one input node, in an autoencoder model, this high-dimensional information gets corrupted by sequentially compressing the input vector into a lower-dimensional representation, which may be called bottleneck layer or embedding. This corrupted lower-dimensional representation now may be used to reconstruct and predict the original input vector. Based on how well the embedding predicted the actual input, the parameters in the network get tweaked and optimized. And eventually, by iterating many datasets through this stochastic process, the autoencoder learns most critical and important variables that determine very distinct properties of a dataset, such as, for example, patient characteristics. Or statistically spoken, these variables should be the ones with the highest variance in the dataset, and these may be highly attractive candidates to include in your propensity score model. To test how well such an autoencoder-derived propensity score may compare versus standard approaches, we conducted a simulation study in a first-line treated cancer population comprising 128,000 cancer patients. Lazoo yielded on average the lowest deviation of resulting estimates, followed by the autoencoder approach. Altering the hyperparameter setup in sensitivity analysis, the autoencoder approach led to similar results as Lazoo. To illustrate the application of the autoencoder-based propensity score, we emulated the 2015 published PRONOUNCE trial by applying the trial's protocol elements within an observational database setting, comparing two chemotherapy regimens. In this case study, all methods provided a similar conclusion with point estimates clustered around the null, with the autoencoder-based hazard ratio being 1.01 as compared to the original trial's hazard ratio of 1.07. In conclusion, we found that the autoencoder-based propensity score computation was a feasible approach to control for confounding, but did not perform meaningfully better than some of the established approaches such as Lazoo.